All right, well, welcome everyone. I am JJ. Let's tackle an example problem. So we're trying to do centroids using integration today. So use integration to determine the centroid of our triangular region that we have shown here. And then all of our distances were in centimeters, 30 centimeters. Let's come in and go through that. I've listed out here what are our steps if we are using integration that should get us through any one of these problems. So the very first thing we need to do is let's get an equation for the top of our shape, the slanted line here, and the bottom of our shape. If we're dealing with that top, let's call this y top. I'm going to say that equation for the top, I'm trying to get a y equals for this. Y top, well, I just have a straight line in here, right? I know the equation for a straight line is y equals mx plus b. So I just need to figure out what are these two variables. What are m and b for this line, and I can get that set up. B is our intercept. I'm hitting right here at the origin. So I know that b should be equal to 0. M is the slope, our rise over run. M would be 15 divided by 30, or that is 0.5. So really this equation for y top here is going to become y top equals mx, 0.5x, plus b, plus 0. Or just y top is 0.5x. With that one known, I can then say, what's my equation for the bottom of the shape? For this bottom line here, we're on the x-axis. That y bottom would just have to be equal to bottom equals 0. And that's our first step. What's our equation for the top and bottom of our shape? From here, we're going to come in and say, I need to set up a differential element on here. This is like in calculus where you said, hey, I could make a really tiny rectangular strip, and I could integrate to sum up all of those strips. Is eventually where you went with integrals for everything. We're kind of doing that same idea here. So I need to come in and say, well, let's set up a differential strip in here. And we're going to exaggerate how big this is just to make it easier to label. But so let's come in and just draw a horizontal line right here. Then we're going to drop down from that to our x-axis, from the top of the shape down to the bottom of the shape. Again, this is loosely just approximating our shape right now. If we got these infinitely small, we would have something that perfectly fits, and we could put one of these everywhere in here. But the very middle of this shape, that's just an x-coordinate and a y-coordinate. We've gone over x, up some y distance. This is x, y. And that's our differential element in here. We want to figure out what's our area of this differential element, though. So we can come in and say, if we're looking for the area of our differential element, we're going to call that dA, the area of a differential element. And that will always just get us what's our y top minus y bottom times dx. So our dA is just going to be, my pen's dripping, so I'm trying to get to follow me. dA is y top, 0.5x, plus y bottom, 0, times dx, or just 0.5x dx. And that'd be our next piece we need there. From there, I can come on and say, let's locate the centroid of our differential area. Where's the centroid of our rectangle located at for this? So let's kind of just put a dot right where that would be at. Our centroid for a rectangle is the very center of it. Always for a rectangle, dead center. If we're thinking through a couple distances in here, well, from that centroid down to the bottom of our shape, or from the x-axis to the x-axis, we're going to call that y bar EL, where the bar means we're saying that's our centroid distance. EL means it's to the centroid of this differential element. And I can get that same thing if I go back to the y-axis. I'm now going in the x direction, so we call this an x bar EL, an x distance to the centroid of our differential element. But again, as we're coming in and setting that up, really what I want to find is where's that located at. Every single time in here, that x bar EL, it's just directly going to measure to directly below x. So our x bar EL for this setup is always equal to x, equals x. Y bar EL is a little bit trickier, but we can always say, well, that's halfway in between the top of our shape and the bottom of our shape. Really, if we're doing that, we can just say, well, that's y top plus y bottom divided by 2. We're averaging out the top and the bottom coordinate by doing this. It gets us the midpoint. That's all an average really is doing. So our y bar EL should be our y top, 0.5x, plus our y bottom, plus 0, so let's just leave it off, divided by 2. Or this y bar EL is going to get us y bar EL equals 0.5 divided by 2 is a quarter, 0.25x. And that takes care of our fourth step, step D. From here, we can start making a couple integrals. Really, if I say I could put in an infinite number of these, if I integrate, it would sum all of them up and get us answers out for everything. So my first thing is, let's find the total area of this shape. So if I'm looking for A, my area should be the integral of dA. dA is set up with an infinitely thin width in the x direction. Really, we could come in and say that width of this, let's call that dx. An infinitely thin strip in our x direction. I could have an infinite number going along the x-axis in here. So I'm going to integrate in that x direction. If I have dx, integrate from the smallest possible x value, that'd be 0, to our largest possible x value, which would be 30. So our integral from 0 to 30 of dA. But I have an equation for dA, 0.5x dx. 0.5x dx. Which I can come in and try to evaluate that. Setting this up, I would get my integral is 0.25 x cubed, and we'd evaluate that from 0 to 30. 0, 30. Which I could come in and solve that. I have a definite integral in here. I would get out from this that my area is 225 centimeters squared, not cubed. Centimeters squared. We also could have done this. This is an easy enough shape. I could have just said, well, my area is 1/2 base times height. 1/2 of 30 times 15 is 225. Really, our work up to this point somewhat is just saying we can use calculus to find the area of a triangle. We knew how to do that probably since we were in elementary school. But we can do it here as well. With a more complicated shape, we probably couldn't just say, oh, I knew that years ago. Let's just apply a known formula. But this would always work for us, this process in here. From there, we're going to come in and find our QI and QX. These are just going to become the numerator in our centroid formulas. If you go on and you take mechanics and materials, these two things, QI and QX, become really important as we're dealing with how objects fail a little bit. And it's really just coming down to centroid type calculation still. This keeps showing up for us. Let's go ahead and find those. QI, I know that QI is my integral of x bar EL dA. My x bar EL is just x times dA times 0.5x. Or this will be the same thing as multiplying our x's together, their integral of 0.5 x squared. Either way, we're still using, I need to get a dx in there, don't I? Let's add dx in and then rewrite that. 0.5 x dx to fully pull in what we have for dA. Or this is 0.5 x squared dx. Either way, though, I'm going, since I have dx, from the smallest x value, 0, out to my largest one, 30. So we're still integrating from 0 to 30 on this. With that set up, we can then say, well, how do I actually evaluate that? If I come in and I take that integral, I'm going to get that QI will solve out to get me that it is 0.5 x cubed divided by 3, and we'd evaluate that again from 0 to 30. We're getting our definite integral out here. Our QI value is going to get us to 4,500 centimeters cubed. Our Q values are going to feel a little bit abstract. Don't stress out about what they actually are meaning here. They are just the numerator for our centroid formula. So we're just trying to make this kind of easy to work with pieces. I can do a similar thing for QX. QX, I know, is my integral of y bar EL times dA. So my integral, I'm still going to end up, since I'm using dA, I have a dx, so I'm going to go from 0 to 30 of y bar EL, 0.5x over 2, or really that's 0.25x equals 0.25x times dA, times 0.5x dx. Or I could, again, combine my like terms. 0.5 divided by 4 is an eighth, x squared. So I have, this is my integral of, if I do that all in one go and evaluate this, we'd really just get this is x cubed over 8 evaluated from 0 to 30. Because this simplifies to x squared over 8 dx. But this will get me my qx. Qx is going to be equal to 1,125 centimeters cubed. And that gets me everything I need. I have qx, qy, and my area. I can find my two centroids. And then we'll talk through a little bit on does this make sense for us. But x bar here should be, x bar is qy over a, 4,500 divided by the area in here. Our total area was 225 over 225. Or our x bar is going to get us to 20 centimeters. 20 centimeters. Which should be our first answer. And we can repeat that general process for y bar. Our y bar should be, our equation is qx over a. So qx I know is 1125. 1125 over my area. My area is still 225 over 225. Or y bar ends up getting us to 5 centimeters. Which would be our second answer in this. Logically, we should have been able to predict this a little bit. We have used centroid a couple times leading up to this point in our course. Really, we've used these for triangular distributed loads, where we said a triangular distributed load has its force acting at the centroid. If we think of this, if we erase something super quick here, if we think of this triangle not just as a random area, but as a distributed load, I could put in a whole bunch of arrows coming down in here. And if I were to ask you, hey, where's that centroid? Where's this distributed load going to act at? We probably can all say, oh, it should be a third of the way in from that 90-degree angle. That 90-degree angle is back on this corner. A third of the way into that, well, if I measure from here, that would be 10 centimeters in. But a third of the way from that point, or from the 90-degree side, is 2/3 from the pointy side. That would get me 20 centimeters coming in. That's exactly what we got for our x bar. We're acting at the centroid in here. And if we turn this distributed load so our arrow's pointed to the right in here, we would say our y bar should be a third of the way up into the triangle from the 90-degree corner. A third of 15 would get us 5, would be our distance to where this ends up acting at. But hopefully this is a useful video for you. If it was, stick around, hit those like and subscribe buttons, watch more videos. Let's get you an A with JJ.